Okay, all right. So let's start the new module. And okay, so in this module, we will explore how the IoT edge devices are deployed. So the main thing is how the edge device is deployed in the uh, real industrial environments, and how the data flows between the edge device and the cloud and on-premises infrastructure. Okay, so how the data flows between the edge, the cloud system, and the on-premise infrastructure. Okay, we will we'll we will walk through the common deployment patterns. Basically, what we are going to see is we will be looking at different deployment or cases, and we will consider the how the different factors, latency, bandwidth, resilience, and scalability are acting. Okay, so understanding these scenarios is essential for designing reliable, secure, and cost-effective IoT solutions. So here is a diagram. This diagram illustrates the hierarchical structure of the data source in an industrial plant, highlighting where data is generated. So the data is generated here. Okay, so the data is generated here and how it flows through the network. From the bottom, we have the field devices, sensors, the valves, the pumps, the motors, and they are all connected to via the field bus. And they are all connected via field bus protocols to the sometimes the microcontrollers, the PLCs, and even the DCS systems. Okay, and these controllers are sending data upward to the control via the control bus to systems like, for example, the SCADA systems and the OPC servers, and these actually aggregate and visualize the data. So they actually uh, aggregate and visualize the data at this layer, and then the data is further transferred via Ethernet to the enterprise layer. So in enterprise systems like MES, this is the enterprise layer, MES, where we have the asset integrity, asset registry, and ERP platforms. So the question can be where and how to connect the edge. Okay, so now if you see on the edge device, every device is placed just before the firewall. We see here, this is the firewall, and then the edge device is just placed here just before the firewall and connected over the Ethernet to intercept and analyze the data before it reaches the cloud. It can also be connected to the OPC server here, where it can tap into the standardized industrial data flow for pre-processing, analytics, and secure transmission. So this configuration allows edge devices to filter and analyze data locally, reducing the latency and network load while enabling the real-time decision. Uh, so in this slide, we see that how the logical uh, schema of industrial plants industrial plants IoT system is not complete representation of the devices and protocols and networks. It is important to recognize that this schema is only one way to understand their interaction and interconnections. So the devices initially placed at one level in the architecture may be reassigned to the other levels depending on the operational needs. Okay, either expanding or limiting their scope. So with technological advancements, devices are now offering enabling additional capabilities and also the computing power. So this flexibility, basically the flexibility. So the flexibility is key in modern IIoT systems, where the main thing is scalability and adaptability are essential for optimal performance. Okay, so this slide um, brings us three common methods for connecting the edge devices in industrial sources. Okay, how in industrial sources we can connect. So in this case, the edge is connected to the field bus protocol. In this case, the field device communicates directly with the controllers like PLCs and DCS systems using the protocols like, for example, the Modbus and Profibus, TCP/IP, Ethernet, uh, e- Ethernet IP. So this is suitable for direct data acquisition from the control devices without an intermediate OPC layer. Then we have the edge connected to the OPC server. This edge connects to a centralized OPC server that aggregate data from the various sources. This is popular and is standardized method. And this is what we are also doing in the project, providing the structured access to the process variable. The third one is the connecting the edge connecting to the OPC server running on the controller. So some modern controllers have built-in OPC UA servers. Some of the PLCs they have it. So the edge device can directly pull data from the controller, reducing the latency and simplifying the architecture. So controller itself is having the OPC server. So these deployment options depend on the plant infrastructures. These are all. So which one we are going to select? The selection depends on the plant infrastructure and communication protocols. uh, Protocols in use, and also the level of like abstraction required at the edge. Okay. Okay, so in this okay, so in this first structure architecture, the edge device directly interfaces with the PLCs and the DCS systems. Okay, so through the field bus protocol. So this means that the edge must support the industrial communication standards like the Ethernet IP or Profinet or Modbus. These connections allow the edge to extract the real-time operational data from the cloud. And this diagram shows the edge device, which is labeled. If you see this, it's already labeled that this is a Profibus field bus connector is there on the edge device, and it is tapping into the control layer of the automation hierarchy. So while it appears straightforward, implementing and maintaining these low level protocols is complex. Okay, this is a complex to maintain at the edge, and it requires careful configuration compatibility with the industrial existing setup, and I think it is more expensive. The edge devices that are doing this are that coming with field bus are expensive. So this setup is useful in plants, very useful. It is useful and desired. Okay, but because there is no OPC server is available right now, so if no OPC server is available, then this is the very useful solution for the plants, where we can directly access uh, without any latency issues. Okay, and And here are the strengths and weaknesses of connecting directly the edge to the field bus protocol. So what are the strengths for this system? First, we gain the direct access to the controller, and this makes sure that we have the high accuracy of data from the most trusted source directly, first-hand information. And secondly, the edge device handles both data acquisition and data forwarding, so it is more reliable, reducing the reliance on other devices in the middleware. And the third point is that the architecture has only two primary interfaces. So one interface to the PLC or DCS, and the other to the cloud. So which simplifies the communication and improves the stability. So it is more stable and more reliable, especially when we combine it with the store and forward buffering. There are also little weaknesses about it. For example, the major limitation is that the tight coupling to the field protocol. So as it is tightly coupled with the field protocol like Modbus or Profibus, so it requires dedicated you can say that the connections or the connectors. Okay, so dedicated connectors, even dedicated connectors and drivers. Okay, so it makes your system less flexible. Okay, and it is also hard to maintain. Okay, so it is hard to maintain and less flexible, especially when working with heterogeneous environment. Heterogeneous means you have devices from different vendors. Okay, now let's talk about an important challenge in this architecture, the need of more edge devices. So the more edge devices are needed, usually a single PLC or even a full-fledged DCS does not control the entire industrial plant. So it typically covers only a specific area. For example, the many in many setups, a DCS acts as a main concentrator and handling the control operations for one part, but not the entire facility. And here is the issue: so these control systems are not interconnected. So if we have DCS, it will be maybe controlling, let's say, 50% of the plant. Okay, for certain reasons. So the issue is this is actually by design. Some limited security risk can reduce not all these control systems are interconnected. So there may be DCS1, then there may be some PLC that may be doing some 10% of the work. Okay, 10% of yeah, some plant utility, and so on. So these systems are sometimes not all systems are interconnected. Okay, so not all are from same vendor, from same vendor, and also not interconnected. Okay, so one you cannot just focus on one DCS. Okay, so we may have multiple. So they work independently. So they work independently. Okay, and their data is only combined later at the higher level, and their data combines only at SCADA level, for example, or historian, or even historian. So what does that mean for us is when we want to deploy an edge device, it means that we cannot just install one edge node for the whole plant. We must deploy separate edges. Okay, so we need more edge devices for each isolated the control network, and We must deploy separate edge device for each control network if we want to collect all the data from it. And this is scattering of the control network increases the number of edge deployments. So the edge deployment increases in this scenario. The more nodes means more devices to configure, more software to manage, and more maintenance headaches. So while fieldbus-based architectures may seem simple at first, in reality it introduces complexity. So when scaling across the large distributed network, okay. So this is an important point for this. Another major concern is the security. So when we connect an edge device directly to both the control network and the internet, we are violating the fundamental principles of the industrial control system security. We are violating fundamental principles. According to the industry standards, you should never connect the control network directly to the internet. Okay, and we will discuss more on this in the next topic. So instead, the edge device should be placed in what is called demilitarized zone, DMZ. So we will go into more detail on this in the next topic. But the key idea is that DMZ acts as a security buffer between the internal control systems and the outside the world. So to achieve this separation, we need at least we need two firewalls, and one firewall protects the one firewall protects the path toward the internet, and the other controls the access toward the control network. So layer network, this dual layer network uh, is necessary to prevent the cyber threats from reaching our industrial systems. But isolating the control network like this is not straightforward. Um, and we need specialized firewalls, and we call them operational firewalls, which are designed to understand and inspect traffic from the protocols like the field buses and the Profinet or the mod buses. So even when all of this is in place, the firewall, the DMZ and the security policies, many companies still choose to disallow this type of setup, and that's why, and this is one of the biggest problems in the transformation of IoT or Industry 4.0. So their internal cybersecurity standards often prohibit any device that bridges the control network and the internet even indirectly. Okay, so now let's look at the second connection scenario. In this connection scenario, we have edge connecting to the OPC server. This is widely um, considered the most ideal and preferred setup. And this is preferred setup. And here the edge device is connected to, is acts as an OPC client. This is then acts as a OPC client here, and it connects directly to the OPC server. And this is powerful because it lets us fully utilize the advanced features of OPC UA, such as the security, data modeling, standardized data access. We have all seen this. So this kind of setup brings flexibility. And so this is flexible as well as secure. Okay, the OPC server could be collecting data from any of the PLCs or SCADA or DCS. Okay, and even the historian, it can collect data from there. So regardless of where the data originates, as long as it is being exposed to the exposed via the OPC server, OPC UA server, the edge can directly easily consume it, and using the OPC client interface to send and collect the data. So it is important to note that this direct connection simplifies the architecture. So this simplifies the architecture, and it is preferred. And somehow it is cost effective. Okay, and it removes also the need for protocol conversion and additional converters. Now let's go over the key strengths of OPC UA for the edge connection. The first is the OPC interface abstracts the underlying device, underlying protocols, so the edge does not need to worry about which Profibus, which field bus protocol the data originates from. It only talks to the OPC UA server. That means no need for the field bus specific connectors. This is very interesting. We don't need to worry about the specific connectors and making the edge setup simpler and more flexible. Okay, so the edge connection is simple and flexible. Okay, then the second point is about the OPC UA server can serve as like a hub. It gathers data from multiple PLCs and DCS. So instead of deploying one edge per controller, we can just one edge to connect to a centralized OPC server and access data from several control systems at once. So that significantly reduces deployment efforts. The third point is about, since the edge is not directly connected to the control network, we can safely place it in DMZ area as per the ICS security guidelines. So this improves the both security and compliance. So this way, this method actually improves uh, security and compliance without compromising without compromising data availability, right? Okay. So while connecting the edge to OPC server is quite powerful, we should also consider some of the weaknesses of this setup. The first weakness is that the OPC UA server acts as a central node. Okay. So when it acts as a central node, okay, collecting all the data from many sources. So if that server goes down, the entire IIoT data flow breaks down. Okay, so the entire IoT data flow breaks down. Give me a minute. Okay, yeah. Okay, so the entire IoT data flow breaks if the server is breaks down. So we risk losing access to the data from all PLCs, DCs, SCADA that were feeding into it. So this makes the OPC server a single point of failure. Okay, so this is important. Single point of failure is an issue here. Secondly, even if we experience only partial data loss, it can be hard to pinpoint the source of the issue. So if there is some data issue or issue with some data, pinpointing that data source will be a problem. So since the data is aggregated at the OPC level, okay, so as the data is aggregated on OPC server, so tracing the exact underlying controller or system causing the disruption becomes challenging. So while OPC UA offers flexibility, scalability, and sort of robustness monitoring, redundancy becomes essential to ensure the uninterrupted. So what we can do is we have to add more OPC server in a redundancy mode. Okay. Okay, let's continue. Uh, Now let's look at the third architecture for the deployment. The edge is connected to an OPC UA server running directly on the controller. So the OPC UA server is exactly running on a PLC. We discussed that some vendors they are now providing the PLCs which have the OPC server on. So OPC server on PLC. Okay, so in this setup, the OPC server is provided by the PLC or DCS vendor, and it runs on dedicated board, usually installed on maybe in one of the racks. Okay, this may be the OPC UA server card or board, which is installed on the one of the PLCs. So now this is um, this serves this server can handle the field bus protocol used by that specific controller, and now this is growing trend. Many modern PLC vendors are natively offering OPC server support built into their hardware. So this simplifies the integration since the edge device can act as a OPC client and connect directly to the controller and retrieves all the necessary data without needing extra converters or gateways. And by this, we know exactly if there is a problem, we know the source. Okay, so the source directly getting the data from the source. So this approach is streamlines the setup and allows for a tighter integration between the control and the edge. So this is the tighter integration between edge and controller like PLC. Okay. Okay. So this is the last. These are the strength and weakness for the last setup. For this setup, when edge is connected on to an OPC UA server, and this OPC UA server is directly hosted on the controller. So first is it limits the data access to only one specific controller. Okay. So because industrial networks are usually segmented and isolated for security, so the edge device would not be able to access other UAPs, OPC UA servers hosted on the different controllers. So the OPC UA will be isolated. So this can be challenging in large plants where data is scattered across multiple vendors, multiple controllers. However, from a firewall management perspective, this setup is quite straightforward. Since the OPC UA traffic is based on standard TCP or HTTPS, firewalls can handle this easily with the basic rules or settings. So there is no need for deep packet inspection like we do in the Profibus protocols, field bus protocols. One concern to note though is some of the OPC servers allow the client um, allow clients to connect without secure modes, especially when the security mode is set to none. Okay, sometimes we configure and we keep it to none, so that raises a security issue. Security security issue, and um, and the field engineers might hesitate to connect a PLC to the edge device if it is exposed to the internet, because PLC is okay, but through the edge, it may indirectly bring some cybersecurity issues. So while this option brings convenience, we have to be careful. So the most important critical thing is, or weak point is, it is potential uh, um potentially uh, weak point from security security aspect if if not configured properly for security. Okay, because edge is directly connecting to the PLC's OPC server. Okay. Thank you very much. So next slide, we will discuss about a case study. So we will stop it here now.